Hello everyone, my name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is to draw the Lewis structure of NO2 minus. Okay. Give me 1 second. Okay, sorry about that. My pen died, so I'm just charging it now. So, the Lewis structure of NO2 minus. So when we write the Lewis structures, we first have to find out the total number of valence electrons. In the case of nitrogen, nitrogen has 5 valence electrons. And in the case of oxygen, each oxygen atom contains 6, and there are 2 oxygen atoms, so we multiply this by 2. And also this is an ion that has a -1 charge, so I need to add an extra electron as well. So if we add this all up, we have a total of 18 electrons. So now I'm just going to rearrange my atoms so that nitrogen is in the middle as our central atom. And then I'm just going to draw 2 bonds to oxygen on either side. Okay, so at this point, I would try to write in all of the lone pairs on my terminal atoms. So in this case, all of the oxygens. And to have a full valence shell, we would need 3 lone pairs in total. So notice that nitrogen still does not have a full valence shell. So instead of making both oxygens single bonded, I'm going to make one of them double bonded. And at this point of drawing, I just like to see how many electrons I've drawn down so far. So if we recall that each bond contains 2 electrons, and we have 3 bonds, I have so far drawn 6 electrons participating in the bonds, and now I'm just going to count on my lone pairs. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I need 2 more electrons, so the last 2 I'm going to put as lone pairs on my nitrogen. Okay, so now that I drew out this structure, I want to find out all of the formal charges for each of these atoms. Let's do this down here. So formal charge will help us see, obviously, what charge each atom would have. And its equation is the number of valence electrons minus the number of non-bonding electrons. So these are all the electrons in the lone pairs. And lastly, the number of bonding electrons divided by 2. Okay, so I'll label the 2 oxygens 1 and 2. So let's calculate the formal charge of the first oxygen. Formal charge of oxygen 1. So the number of valence electrons in oxygen is 6. Its number of non-bonding electrons is 4. And its number of bonding electrons, so there are 2 double bonds. So we have 4 in total, and this is divided by 2. So 6 minus 4 minus 2 is equal to 0. So now let's look at the formal charge of nitrogen. So nitrogen has 5 valence electrons. The number of non-bonding electrons nitrogen has is 2. And there are 3 bonds to nitrogen, so there are 6 bonding electrons divided by 2. So 5 minus 2 minus 3 is also 0. And now let's look at the formal charge of our last oxygen. Again, oxygen has 6 valence electrons. This oxygen in particular has 6 non-bonding electrons, and there's also 2 bonding electrons in that single bond. So the formal charge of the last oxygen is -1. So I just need to write a charge on this one oxygen. And this is one of the resonance structures of NO2. And I can draw a second one with the other oxygen. With the leftmost oxygen now carrying the negative charge. Okay, so these are the 2 Lewis structures of NO2-. And the junior tutor said that the Lewis dot structure represents the arrangement of electrons, shown as dots, between atoms in a molecule. Atoms must follow the octet rule, or the tendency of atoms to prefer to have 8 electrons in the valence shell. The individual formal charge of each atom, as well as the overall charge of the molecule, must be satisfied. In drawing the electron dot structure of NO2-, we first draw the skeletal structure. with the nitrogen in the middle. Nitrogen is less electronegative than oxygen. And also we kind of can estimate which atom is the central atom just because there's only one of it and there's two oxygens. Step 2 is to calculate the total number of valence electrons in the molecule. So we did this first, but it doesn't really matter what order you do the steps in. Step 3, distribute the electrons as dots. Step 4, to satisfy the octet rule for the nitrogen, a pair of electrons from one oxygen must be transferred. Step 5, replace the shared electrons with bonds. A lone pair of electrons will be left at the top of the central nitrogen atom. And step 6 is to determine the formal charges in each atom. And they got 0, 0, and -1. Okay, so this solution is correct. Okay, so step 2. Step 2, what is a combustion reaction? Okay, so I'll write down a brief definition on what a combustion reaction is. So a combustion reaction is when a substance burns in the presence of oxygen. And the products of a combustion reaction are carbon dioxide and water. And then I'll just say in brackets that this is how energy is produced as well. Okay, so typically the substance that takes place in a combustion reaction are like hydrocarbons. So hydrocarbons just contain carbon and hydrogen. Sometimes even like alcohols can take place in a combustion reaction. But I'll just have an example of a hydrocarbon that is combusted. So let's say we had hexane, which is C6H14, and it's a liquid maybe, plus oxygen, gas, and this produces carbon dioxide and water. I'll just put the states in as well. Okay, so now let's try to balance this equation. I like to first balance my carbons, since carbon is only present in the hexane and only in the carbon dioxide. So I just like to balance carbon first. So to do this, I'll just put a coefficient of 6 in front of CO2. Okay, so after I balance my carbons, then I like to balance out my hydrogens. So there are 14 hydrogens in our reactant side, so I need to put a 7 in front of H2O in order to balance out all the hydrogens. Okay, so notice that when I balanced both my carbons and my hydrogens, this affected the number of oxygens. So this is why I balanced my oxygen last. So first I like to count out how many oxygens are in my product side. So we have 12 plus 7, which is 19. So I put 19 in front of O2, and then I just divide that by 2. So now step 4 is to multiply. If we wanted to get rid of that fraction, we need to multiply the whole reaction by 2. And we are left with the following balanced equation, where 2-hexane plus 19 oxygen produces 12 carbon dioxide plus 14 H2O. Okay, so let's see what the junior tutor said. A combustion reaction occurs when a substance, usually a hydrocarbon, burns in the presence of oxygen that releases energy in the form of light and energy. For complete combustion of hydrocarbons, the products are carbon dioxide and water vapor. However, if the combustion is incomplete, it produces toxic gases such as carbon monoxide. So for example, the complete combustion of propane is represented by the following balanced chemical reaction. So here they have propane, C3H8, plus oxygen produces carbon dioxide and water. So this solution is correct. Okay, so question number 3. Below is the Lewis structure of nitrogen, N2. Count the number of bonding pairs and the number of lone pairs around the right nitrogen atom in this molecule. So I'll show the nitrogen molecule. They are 2 nitrogens with a triple bond, each containing a lone pair. So for this molecule, they wanted us to count the number of bonding pairs. So I'm assuming they mean bonding pairs of electrons that are present in the bond. I'm just going to put that in brackets. Present in the bonds. If that were the case, then we have 3 bonding pairs of electrons. For the number of lone pairs, on the right nitrogen atom in this molecule, there is only 1 lone pair. Okay, so if we wanted to find out the hybridization of this molecule, then we would use the Vesper theory, where you would just look to see how many bonded atoms you have for a certain atom and how many lone pairs. So let's try to use this Vesper table to find out the hybridization of N2. Okay, so we have, it generally looks like the first row, where we have, we have 1 bonded atom and 1 lone pair. So this gives us a linear molecular shape and also a linear electron geometry. And we can also kind of see that in the Lewis structure as well. And we can see its hybridization is sp hybridized. And the bond angle between the two atoms is 180 degrees. Okay, so let's see what the junior tutor said. The given Lewis structure of N2, looking at the right nitrogen molecule, it has 1 lone pair of electrons and 3 bonding pairs of electrons. Okay, so this solution is correct. Okay, so question number 4. What is the Lewis structure of xenon tetrafluoride? Also indicate whether it is polar or nonpolar. Okay, so we have xenon tetrafluoride. So to find out the Lewis structure, I'm first going to calculate the total number of valence electrons in the molecule. So xenon, the xenon atom has 8 valence electrons, and a fluorine atom contains 7. And since there are 4 fluorines, we multiply that by 4. And if we add it all up, we should get 36 valence electrons. Okay, so now I'm going to draw out my structure. So assuming xenon is our central atom, I'm going to draw xenon in the middle. And then just the 4 fluorines all around it. And then I will draw in all of their lone pairs. Okay, so it's this point in drawing where I like to count how many electrons I've drawn so far. So if we remember that each bond contains 2 bonding electrons, and we have 4 bonds, so that's 8. And then each fluorine atom has 6 valent electrons. So 6 times 4 is 24. So we have 32 electrons drawn so far. So I need 4 more if our total valence electrons is 36. So I'm just going to draw in my last 4 electrons as lone pairs on xenon. So now this is our molecule. And the second part of the question asks whether it is polar or nonpolar. So I'll just take note down here that the xenon-fluorine bond is polar. But if we look at the overall molecule, where because fluorine is much more electronegative, I can show dipole moments all pulling electrons towards the direction of the fluorine atoms. But since this molecule is symmetrical, all of the dipole moments cancel each other out. So the xenon tetrafluoride molecule as a whole is nonpolar. So its geometry is a square planar, and it's also symmetrical. Okay, so let's see what the junior tutor said. Okay, so they have the same Lewis structure. Xenon has 2 lone pairs using AXE method to determine geometries, which I think is also just the Vesper theory. AX4 E2, I think, which corresponds to a square planar molecule. Square planar molecules are symmetrical, therefore xenon tetrafluoride is nonpolar. Okay, so this solution is correct. The dipole moments in the xenon fluorine bond will cancel each other out. Okay, so question number 5. What is the Lewis structure for I3-? Show all the lone pairs of electrons and the formal charges. Okay, so first let's find out how many valence electrons are in this ion. So we just have iodine, and iodine has 7 valence electrons, and there are 3 of them. And there's also a negative charge on this as well, so I'm going to add an extra electron. And we have a total of 22. Okay, so it makes the most sense if we draw the structure in a line. Okay, so now I'm just going to draw in all the lone pairs of iodine and count out how many electrons I've drawn so far. So let's count this. We have 2 electrons in each bond, so that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, 20. So I only have 20 drawn for this molecule, and I need 22 electrons. So I'm going to put an extra lone pair on our central iodine atom. And now I'm just going to find out the formal charges of each of the ions. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons. So these are the electrons in the lone pairs minus the number of bonding electrons divided by 2. So first, let's look at the formal charge of the iodines that are terminal, so that are on the left and the right of the central one. So since they're the same, that's why I didn't specify which one. So each iodine has 7 valence electrons. The number of non-bonding electrons, so there are 1, 2, 3, 4, 5, 6, minus the number of bonding electrons divided by 2. So there is only one bond. Each bond contains 2 bonding electrons, and then we divide this by 2. So 7 minus 6 minus 1 is just 0. So now let's calculate the formal charge of iodine, and this is going to be our central atom. It still has 7 valence electrons. This time the number of non-bonding electrons, yeah, is still 6. But the number of bonds it has is 2 bonds. So there are 4 bonding electrons divided by 2. And 7 minus 6 minus 2 gives -1. So the central iodine is where I would draw in my negative charge. Okay, so let's see what the junior tutor said. The Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. Drawing the Lewis structure of a compound may sometimes need some trial and error. However, we can follow some guides and rules in drawing it. So step by step, determine the central atom, logically arrange the atoms, connect, make necessary adjustments. And these are some of the rules. So make sure atoms that follow the octet rule strictly have 8 valence electrons. Step 2, minimize the formal charges of the atoms if possible. So we already knew that this had a negative charge, so that's okay. And then the more electronegative atoms are given, the more negative formal charge, if applicable. So all of these atoms are the same, so that rule doesn't really matter for this case. And then 4, make sure the sum of the formal charges match the charge of the compound. So again, for our case, we have a -1 only in the central iodine, and we know that there's a -1 charge in the overall molecule. Okay, so let's see what structure they got. So for the triiodide ion, they got the same structure. So this solution is correct. Yep, so they just went through how they got to their answer. Everything looks good. Okay, so question number 6 is to draw the Lewis structure for carbon tetrachloride. What is the molecular geometry of this compound, and is the molecule polar or nonpolar? Okay, so first let's draw the Lewis structure. So I'm first going to determine the total valence electrons in the molecule. So carbon has 4 valence electrons, and chlorine contains 7, and there are 4 chlorine atoms. So in total, we have 32 valence electrons. Okay, so now my central atom is carbon, and I'm just going to draw the 4 bonds to chlorine. So now I'll just draw in all of the lone pairs on chlorine. And then from there, I like to count out how many electrons I've drawn so far. So if we remember that each bond contains 2 bonding electrons, and there are 4 bonds, then we have 8, and then each chlorine atom contains 6 valence electrons. So 24 plus 8 is 32. Okay, so this is the Lewis structure for carbon tetrachloride. So now the second part of the question asks, what is the molecular geometry of this compound? So to help us answer this question, we're going to use the Vesper theory. And first, I look at my central atom, which is carbon, and then I count out how many lone pairs carbon has. So in this case, carbon has 0 lone pairs. And then I like to count out how many bonds or how many bonded atoms are attached to the carbon. So this carbon has 4 bonded atoms. So now let's look at this helpful Vesper theory table. So total domains is 4. And in this first row here, if we have 4 bonded atoms and 0 lone pairs, both its molecular shape and electron geometry is a tetrahedral. So let's write this down. We have a tetrahedral. So this is sp3 hybridized. And the bond angles are all 109.5 degrees. And the third part of the question asks whether or not the molecule is polar or nonpolar. So in terms of polarity, first I'll just introduce a polar bond. So this is when the difference in electronegativity is greater than 0.4, but also less than 1.69, we have a polar bond. So first I'll just say that a carbon and chlorine bond is polar. Because its electronegativity is greater than 5, but it's less than 1.69. I think I drew these the wrong way. So it's greater than 0.5 and less than 1.69. But if we look at our overall molecule, we can show how these dipole moments can be formed because chlorine is much more electronegative than carbon. But for the molecule, they all cancel each other out. So this makes the entire molecule nonpolar. So the whole molecule is nonpolar because these dipole moments cancel each other out. Okay, so let's see what the junior tutor said. The Lewis dot structure represents the arrangement of electrons, shown as dots, between atoms in a molecule. Atoms must follow the octet rule or the tendency of atoms to prefer to have 8 electrons in the valence shell. The individual formal charge of each atom, as well as the overall formal charge of the molecule, must be satisfied. In drawing the electron dot structure, carbon tetrachloride, we draw the skeletal structure with carbon in the middle, then calculate the total number of valence electrons, so they got 32, draw single bonds between the atoms, and then distribute the remaining electrons as dots following the octet rule. Okay, so they got the same Lewis structure and noted that it has a tetrahedral molecular geometry and the molecule is nonpolar because of the symmetric distribution of electrons. Yep, so this solution is correct. Okay, so question 7. Draw the Lewis structure for COCl2, including lone pairs. What is the molecular shape? Is the carbon-chlorine bond polar or nonpolar? Is the molecule polar or nonpolar? Okay, so first let's calculate the total valence electrons in the molecule, and this will help us draw out the Lewis structure. So carbon contains 4 electrons, oxygen contains 6, and a chlorine atom contains 7, and there are 2 chlorine atoms, so we multiply this by 2. And then if we add these all up, you get a total number of 24 valence electrons. Okay, so now assuming that my carbon is the central atom, because it is the least electronegative, I'm then going to draw all of the terminal atoms. And then from there, I'll show all of the lone pairs on the terminal atoms. Okay, so before I draw the lone pairs on the oxygen, I first like to analyze to see if carbon has a full octet, and you can already see that it does not. So carbon is most likely going to form a double bond with this oxygen, since it's least likely to bond one with the chlorine, since chlorine already has the 7 electrons, it'll most likely form one with the oxygen. So now if I draw a double bond, carbon has a full octet, and our oxygen atom will then just have 2 lone pairs. And then at this point, I like to count out to see if the total valence electrons is equal to 24. So first, let's recall that each bond contains 2 bonding electrons, and there are 4 bonds, so we have 8 plus 4 is 12, 18, 24. So we have a total of 24 valence electrons, so we know that we drew the Lewis structure correctly. So the next part of the question asks, what is the molecular shape of this molecule? So to answer this question, we are going to use the Vesper theory, and we look at our central atom, which is the carbon, and count out how many lone pairs carbon has. So carbon has 0 lone pairs. And then we also count out how many atoms are bonded with the carbon. So if we count, we have 3 bonded atoms, which is the 1 oxygen and the 2 chlorines. So now let's use the Vesper table to find out its molecular shape. So if we look at the total domains, that is 3. So when we have 3 bonded atoms and 0 lone pairs. The molecular shape is trigonal planar. Trigonal planar? And also it is sp2 hybridized. And the bond angle is 120 degrees. And the last, or the third part of the question asks if the carbon-chlorine bond is polar or nonpolar. Bond. Carbon-chlorine bond. So to find out whether or not a bond is polar or nonpolar, we need to calculate the difference in electronegativity of carbon and chlorine. So let me search electronegativity values. Spelled that wrong, but let's look at this. So the difference in electronegativity of a carbon and chlorine bond. So chlorine has an electronegativity of 3, and carbon's is 2.5. So the difference is 0.5. And this means that the bond is polar. And we know a bond is polar when its electronegativity difference is greater than or equal to 0.5. But less than 1.69. And we also know if something is polar when it doesn't contain any metals and it's just 2 nonmetals. And the last part is the molecule polar or nonpolar. So if we were to draw out all of the dipole moments that are formed because of these more electronegative atoms, you'd get this, the chlorine pulling in its direction because chlorine is much more electronegative than carbon. And oxygen is also electronegative as well, and it will have a dipole moment of its own, but it probably won't be of equal strength to the 2 chlorine atoms. So they all have different dipole moments and they don't cancel each other out. So the molecule as a whole is polar as well. Is polar. Dipole moments do not cancel out. Okay, so the junior tutor drew the same Lewis structure, and then they wrote out their electronegativity values of both carbon and chlorine. Okay, so the values they used had much more significant figures, so they were able to more accurately find an electronegativity difference of 0.61, which is greater than 0.4. So therefore, this carbon-chlorine bond is polar. The shape of the molecule is trigonal planar, and dipoles do not cancel out, therefore the molecule is polar. Yep. So this solution is correct. Okay, so question number 8. What is the Lewis structure? Assuming that's PO4 minus 3. So the phosphate ion, in which the octet rule is satisfied on all atoms, show all the non-zero formal charges. And the second part, in which the central phosphorus atom has a formal charge of 0, show all the non-zero formal charges. Okay, so first let's calculate the total number of valence electrons. So a phosphorus atom has 5 valence electrons. Oxygen has 6. And there are 4 oxygens. So we multiply 6 by 4. And there's also a minus 3 charge, so we add an additional 3 electrons. So this gives us a total of 32. Okay, so for the first part of the question, they want us to draw the Lewis structure in which the octet rule is satisfied on all atoms. So let's draw the phosphorus in the middle. Let's do this as A. Where the octet rule is satisfied. So if we were to draw phosphorus in the middle with all of the oxygen atoms symmetrically placed around it, then our phosphorus atom has its octet rule satisfied. And if I were to draw all of the lone pairs on oxygen, then each oxygen atom has the octet rule satisfied as well. So now they want us to show all the non-zero formal charges. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons. So these are all the lone pairs, minus the number of bonding electrons divided by 2. Okay, so let's calculate the formal charge of phosphorus. Phosphorus has 5 valence electrons. There are no lone pairs, so no non-bonding electrons. And there are 4 bonds, so there are 8 bonding electrons in total. So 5 minus 4 is plus 1. So we'll put a positive charge on the phosphorus. And we only need to calculate the formal charge on one of the oxygen atoms since they are all the same. So oxygen has 6 valence electrons. The number of non-bonding electrons is also 6. And the number of bonding electrons is 2, since there's only one single bond attached. So 6 minus 1 is -1. So all of the oxygens has a -1 charge. So this is the structure in which the octet rule is satisfied on all atoms. And for part B, in which the central phosphorus atom has a formal charge of 0. So in order for the phosphorus to have a formal charge of 0, I'm going to form a double bond with one of the oxygens. So now all of these oxygens still have a -1 charge because they didn't change. But now let's calculate the formal charge of this double bonded oxygen. Oxygen in the double bond. It still has 6 valence electrons. Its number of non-bonding electrons is only 4 this time. Oops. And there are 2 bonds because it's a double bond. So we have 4 bonding electrons divided by 2. So 6 minus 4 minus 2 is just 0. And now let's double check to see the new formal charge of our phosphorus. Still has 5 valence electrons, 0 non-bonding electrons. And now if we count out all of the bonds, we have 1, 2, 3, 4, 5. So we have 10 bonding electrons divided by 2. And this gives a formal charge of 0 on our phosphorus. So that is correct as well. So now let's see what the junior tutor said. They summarize the Lewis structure. And for part A, they got the same structure where the octet rule is satisfied. And for part B, they drew the double bond to show that phosphorus is now neutral. So this solution is correct. Okay, so question number 9. What is the electron configuration of phosphorus in its ground state? So to find the electron configuration of phosphorus, we first need to divide our periodic table into the different orbital sections. So the light blue is the S block, the green is the P block, the orange is the D block, and the pink is the F block. So starting from hydrogen, we move left to right up to the atom or the element that we're looking for, which is phosphorus. And as we go down the periodic table, we write the block number or the row number followed by the block letter. And in the superscript, how many electrons are in that orbital. So let me just quickly show, starting from hydrogen, we have 1s2, and then going down to the lithium, 2s2, and then moving across, 2p6, and then 3s2, and then up to the phosphorus, we count 3p, 1, 2, 3, 3. And if we wanted to write the shorthand configuration, we find the noble gas that comes before phosphorus, which is neon. So you just put that in square brackets. And then you kind of continue on the same way you'd normally do. Neon 3s2, 3p3. So this is the electron configuration of phosphorus. The junior tutor said that electron configuration is a notation that shows how electrons are distributed in an atom or in the molecule's orbitals. There are 7 principles that govern how electrons occupy the orbitals. One of these is the Aufbau principle, which states that electrons occupy the available orbital with the lowest energy. So this is another method of writing out your electron configuration, and you kind of just move diagonally and write it in order. And phosphorus atom has 15 electrons. Write the electron configuration for this. We have to arrange the subshells from left to right as dictated by Madelung's rule. After each subshell, indicate the number of electrons as a superscript, and then repeat the process until the sum of the superscripts is 15. Yep, and they got the same electron configuration, so the solution is correct. Okay, and I think we have time for one more question. Is BF3 polar or nonpolar? So let's write down the Lewis structure for boron trifluoride. Boron has 3 valence electrons. Chlorine has 7, and there are 3 of them. So we have 24 valence electrons in total. And we can quickly draw out its Lewis structure. And boron is one of the elements that is an exception to the octet rule, and it's perfectly fine just having 6 bonded electrons. And if we count it all out, we have 24, so everything's good. And the question asks if the molecule is polar or nonpolar. So if we recall, fluorine is much more electronegative, so it's going to pull and have dipole moments in the molecule. But since boron has no lone pairs, everything is symmetrical, so all of these dipole moments will cancel each other out. So therefore, this molecule is nonpolar. And the junior tutor said, polarity refers to the charge separation which causes the presence of dipole moment. Additionally, polarity can be viewed from the perspective of a bond or the entire molecule itself. A bond can be polar because the electrons are unequally shared between the bonded atoms due to their electronegativity difference. So the boron and fluorine bond is polar because of the electronegativity difference. However, although a molecule has polar bonds, this does not imply that the entire molecule is polar. The molecule's symmetry results in the cancellation of the dipole moments. Overall, the molecule becomes nonpolar. So they noted that the molecule contains polar bonds, but when they look at the shape of the entire molecule, the dipole moments cancel each other out. Yep, so this solution is correct. Okay, so those are all the questions. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a thumbs up and a like, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.